Hi boys and girls. This video series comprises the lecture for section 8.8 entitled Improper Integrals, which starts on page 578. We're going to start with the discussion of this type of improper integral with infinite limits of integration. But before we start talking about that specifically, let's define what an improper integral is in general. Notice we start with the definition of a definite integral, and here's a sample definite integral. Endpoints from a to b, f of x dx, requires, see the word requires, that the interval be finite. The interval from a to b be finite. Furthermore, the fundamental theorem of calculus, by which you have been evaluating definite integrals, requires that f be continuous. Requires that f be continuous on AB. In other words, we know that the area under this curve is going to be equivalent to the value of this definite integral, so we want the endpoints of integration to be finite. We want a finite value from a to b. Or we want to make sure that there are no discontinuities on the curve as we're trying to integrate. Well, what if we take those two requirements away? What if we say the interval doesn't have to be finite, or the function doesn't have to be continuous? It seems as though we would be turning the world of definite integrals upside down. But actually, it just introduces the world of improper integrals and how we can sort of sidestep these oddities that are occurring and go ahead and evaluate the integral anyway. We will study a procedure for evaluating integrals that do not satisfy these requirements, usually because one or both of the limits of integration are infinite, or because f has a finite number of infinite discontinuities in the interval. Integrals that possess either of these properties are called improper integrals. So that's just an introduction of what improper integrals are, the two kinds that you could have. And as I said, we're going to start with this kind in our discussion. A final note on this little introduction: note that a function is said to have an infinite discontinuity at C if from the right or left, as you're approaching C in this function, the function value is approaching infinity or negative infinity. This usually happens at asymptotes. Let's say you have the function 1 over x. Maybe you're trying to evaluate from -1 to 1, but you know there's a discontinuity at C. As you're approaching C in this function from the left, since this is what the function looks like, as you're approaching 0 from the left, you can see the function value is tending toward negative infinity. As you're approaching C, the point of discontinuity, from the right, you can see that the function value is approaching positive infinity. So when these things are occurring, we say that there is an infinite discontinuity at a point in this particular function. That's just the definition of what an infinite discontinuity is. Now, if we look at trying to calculate the area under a curve from 1 to b, in this case, notice we're saying b approaches positive infinity, but we're just saying b is like randomly occurring somewhere here, then it's going to require an improper integral. Why? Because one of the endpoints of integration is infinite. Technically, what we're saying here is from 1 to positive infinity, what is the area under this curve? From 1 to positive infinity. It doesn't seem as though we would even be able to calculate an area where we're tending toward positive infinity. But we can with an improper integral. First, we're going to replace infinity, that shouldn't actually technically be an endpoint of integration in an integral, with a letter such as b. And we're going to instead take the limit of this function as b is approaching positive infinity of this integral from 1 to b, and then we could rewrite this as x to the negative 2 dx. Now, taking the limit as b approaches infinity will give us a value for this integral if the function converges. So notice here we've replaced infinity with the letter b as the right endpoint of integration, and so we're going to integrate from 1 to b dxx squared. We end up with this integral, antiderivative, and then from 1 to b, when you plug b in for x, you get -1 over b. When you put 1 in for x, you get +1 or minus a -1, which is a +1. And that can be rewritten as 1 minus 1 over b. Now, take the limit of that function as b approaches infinity. Notice, because infinity will now go into the denominator of a fraction, this becomes a zero term, and our answer is 1. What does this mean? It means that the actual area under the curve from 1 to positive infinity is 1. How is that possible? Well, in calculus, so many things are possible, so many magical things. This improper integral can be interpreted as the unbounded region between the graph of 1 over x squared and the x-axis, at least to the right of 1. And it actually converges and has a definite area, which is 1. Very odd, but so true. This leads us to sort of a summary of a definition of improper integrals with infinite integration limits. This is the first category. Remember, there's another category that we'll discuss later. So if f is continuous on an interval from a to infinity or from negative infinity to b, the limit will simply be, as we replace infinity or negative infinity with a letter, the limit as that letter approaches positive or negative infinity of the integral from a to b f of x dx. If f is continuous on the interval from negative infinity to infinity, then you end up having to divide this into two integrals. There are two endpoints which are infinite here, so we will change this negative infinity to c plus the integral from c to positive infinity, where c is any real number. You can kind of pick where you want the dividing point to be for the integrals. Notice it says that in the first two cases, the improper integral converges if the limit exists. So if we find a limit here, we find that the function converges, we can actually evaluate the definite integral. If not, then the improper integral diverges and just becomes infinitely more large or small. If we look at the third case, the improper integral on the left diverges if either one of these limits diverges. So, but if they both converge, then your improper integral converges. Let's do a few examples now. Starting with example 1 on page 579, let's evaluate 1 to positive infinity dx over x. Now right away I see this and I'm like, improper, cannot have it. So I'm going to change this now to a limit. The limit as b approaches infinity of this integral from 1 to b dx over x. Now you might think, well, why don't I just go ahead and put infinity up there and just plug that in and go and do whatever I need to do? Because the AP readers will not give you credit if you do that. You've got to put this little limit label out on the front. You've got to rewrite the endpoint of integration so infinity is not there for them to give you credit. So as we continue, we're waiting for a point when we can actually take the limit as b approaches positive infinity. At this point, of course, I'm going to integrate this and get natural log of x from 1 to b. Again, I'm just kind of waiting. I can't plug infinity in yet. This is going to be the natural log of b minus the natural log of 1. This, of course, is 0. So I'm really asking here the limit from b to infinity, the limit as b approaches infinity of the natural log of b. When I plug this in, I get infinity. This function diverges, and we are not going to be able to find a finite area. It diverges and there's an infinite area. That might seem dissatisfying, but it did show us something that we needed to know. Now let's look at example 2, improper integrals that converge. Once again, what makes this improper is the endpoint is infinity. Let's replace this with the letter b. The limit as b approaches infinity of this integral from 0 to b, e to the negative x dx. Now to make this right, there should be a negative here and a negative there. This becomes the limit as b approaches infinity of negative e to the negative x from 0 to b. When I plug in b here, I should just keep writing limit as b approaches infinity, but I'm kind of running out of room. I get negative 1 over e to the b. Now notice when I put b in, that becomes e to the negative b, but I dropped that down to the denominator, and of course you're going to understand why in a moment. Minus, and then it's going to be minus this negative, so we'll make it plus e to the 0. Now when we evaluate this, we can see that e to the 0 is 1, and so I'm going to be taking the limit as b approaches infinity of negative 1 over e to the b plus 1. Now let's plug infinity in. Because we put infinity in the denominator, we end up with 0 plus 1, which is 1. So this limit converges, this function converges, and therefore we are able to evaluate the limit and discover that the area between 0 and positive infinity under this curve is actually 1. Once again, kind of crazy, but that's how it works. Let's do another one. Sorry for the coughing. We have another endpoint that's infinity. Let's change this to the letter b as b approaches infinity from 0 to b of 1 over x squared plus 1. You probably recognize this right away as the arctan integral. Now let's just pretend like I'm putting limit blah 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 blah, and then this is going to be arctan of x from 0 to b. And we still have limit, you know, blah blah blah. We've got arctan of b minus arctan of 0. Now at this point you might need to remember, what exactly are they asking us here? Let's figure out what arctan of 0 is. We want to know tangent of what gives us 0. Well, that's going to be where sine is 0, and so on this particular interval it's going to be at 0. So this whole term now goes to 0. So let's take the limit as b approaches infinity of arctan of b. Now plug infinity in and see what we get. Arctan of infinity. Doesn't that just seem bizarre? Well, here's the question they're asking. Tangent of what is infinity? Where is tangent undefined? Remember, tangent function has a ton of little asymptotes all over the place, right? Well, the first one that we come to is where cosine is undefined, where cosine is 0, and that's pi over 2. So your answer here is pi over 2. And that is the area of this region under the curve from 0 to positive infinity. So those are two improper integrals that converged. All right, let's do example 3. We're going to use L'Hopital's rule with an improper integral. Once again, we have a limit, an endpoint of integration that is infinity. So we're going to change this to the limit as b approaches infinity of this integral from 1 to b of 1 minus x e to the negative x dx. Now we are going to have to use integration by parts here. So I'm going to let, in this case, u is going to be 1 minus x, du will be negative dx. We're going to let dv, let me find space for this, just move this little fellow over. Oops, not too far. We're going to let dv be e to the negative x, which means v is negative e to the negative x. So we've got limit, blah, 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 equals, but let's do uv, which is 1 minus x times negative e to the negative x minus the integral of v du, which is negative e to the negative x times negative dx. Now we can sort out these negatives here. Let's make that a positive. Also, let's rewrite this so that we're distributing this negative and we get x minus 1 e to the negative x, let's just say. And then over here we can integrate e to the negative x. Now we're going to get negative e to the negative x, which is going to make this positive. In other words, there should be a negative here, a negative out here, which ends up making that positive e to the negative x. From, remember, 1 to b. Now before I do this, I'm going to make things easier on myself by factoring out the e to the negative x. This is going to leave x minus 1 plus 1, which of course is just x. Now e to the negative x, x, from 1 to b. Remember, this whole limit thing is following us all the way down. We haven't been able to plug infinity in yet, but it's going to happen soon. This becomes b e to the negative b minus 1 e to the negative 1. So let's write this as b over e to the b and then minus 1 over e and apply our limit. As b approaches infinity, plugging that in here and here becomes a problem. We get an indeterminate form, infinity over infinity, which is why we're going to use L'Hopital's rule. We don't need to use L'Hopital's rule with 1 over e because that's a constant. It doesn't even have a b in there. This is the guy that we're trying to deal with. So let's take the derivative. We take the derivative of b, that's 1. We take the derivative of e to the b, it's e to the b. Now let's plug in infinity here. Remember, we also have minus 1 over e, just calmly waiting for all of the furor to die down. When we plug infinity in for b, we get 1 over infinity, which as we clearly know is 0. And 0 minus 1 over e ends up being negative 1 over e. And that is the value of this definite integral. Now it's negative because this is the little region, it's below. Now remember, in this particular case, we didn't do the x-axis minus the function. We were just evaluating the definite integral of the function. So it's not technically area here, and the value of the definite integral is allowed to be negative. Okay, I'm going to stop this video and start another one in a moment just because I don't know what the deadline is. But that's my decision, and I'll see you shortly in the second video.